Okay, so we left off by doing the the reaction of vicinal diols, right? So taking vicinal diol, treating it with something like KMnO4, and we would cleave that bond between them. And for KMnO4, we oxidize their secondary alcohols all the way up to carboxylic acids, and our tertiary alcohol is going to become a ketone. But I kind of forgot to remind you about where vicinal diols come from, right? So you know how to make vicinal diols. You learn how to make them in Organic 1, right? So you make a vicinal diol by using one of two oxidants. So you can use osmium tetroxide, usually catalytic amount, and hydrogen peroxide. And that will add an oxygen to each carbon of the double bond. And because the osmium holds on to both oxygens and puts them on the double bond at the same time, they end up on the same side of the double bond, or of the molecule, either both wedges or both dashes. Right, so you can use catalytic osmium tetroxide and hydrogen peroxide to make a vicinal diol, or the one everyone remembers, right, is cold dilute KMnO4. And again, same thing, the manganese is holding on to the two oxygens and it sticks them on the molecule at the same time from the same side. So here I'll make them dashes, but right, they could both be wedges or both be dashes. They just come from the same side. Now, this reaction, well, the reactions we've been doing illustrate why we always have to specify that to make a vicinal diol with KMnO4 needed to be cold and dilute, right? If you just have a double, what happens if you take this vicinal diol and you add KMnO4 to it, right? You're going to break the carbon-carbon single bond, oxidize those oxygens to two carboxylic acids. We're going to break this bond. We're going to oxidize this to 1, 2, 3, 4, 5. Great. We're going to oxidize it to the two carboxylic acids. So the reason we say, oh, hey, my KMnO4 to make the vicinal diol needs to be cold and dilute is we're hoping that we run out of KMnO4 before it can start reacting with the diol, right? So if I just were to take this double bond and just add a whole bunch of KMnO4 to it, the KMnO4 is going to react with the double bond to make the diol, and then there's a bunch of KMnO4 left over. So now it's going to react with the diol, and you can, in one step, break your double bond and get to the acid because you've added an excess of KMnO4, or you've added just a lot of it. And as soon as you make the diol then reacts with the KMnO4 to get kind of the next product along the line. So that's why it's cold dilute KMnO4 is, I just want this to react with the double bond. I'm going to cross my fingers and hope that it stops and I run out of KMnO4 and that it doesn't react. If you just added like a concentrated or a lot of KMnO4, it's going to just go from the double bond all the way to the acids. Is all right? Excellent. Okay. So we're going to talk about ethers now. Thankfully, there aren't a ton of reactions with ethers, so not a whole lot here, right? So an ether is an oxygen, single bonded to two carbons, right? Kind of your most simple and the most kidnapping ether. It's an ether you put on a rag and you just like take someone down. Right? Don't do that. Kidnapping bad. Right? Usually the carbons here are sp3 hybridized, right? In the simplest cases, right? So if you just had a generic like R, O, R, these R groups are normally sp3 hybridized. They don't necessarily have to be, right? You can have like aromatic ethers, right? Where the one carbon is sp2. You can even have like alkynyl ethers. So you can do a little bit of different stuff, but for the most part, they're going to be sp3 hybridized carbons attached to that oxygen. If you have, if you replace this hydrogen, right, you replace a hydrogen with, so if you replace it with a non-hydrogen, non-carbon, or non-carbon, right, you stop having an ether, right? So, right, something like this, just broadly, not an ether, right? If you start putting different atoms at the carbon bonded to the oxygen, you're going to get different functional groups. So you just have to keep them pretty simple, and you're basically limited to carbons and hydrogens on the carbon bonded to the oxygen. So this, oops, not an ether. It behaves differently because that's not a carbon or a hydrogen. Right? So they don't kind of fit in that broad like ether category when you start putting other atoms on the carbon. Now, you can have, right, this still an ether. I can put a bunch of carbons there, that's fine. But when you start putting heteroatoms, oxygens, nitrogens, halogens, they stop being ethers because they behave differently. Ethers are broken up into two really broad categories based on their structure. Has nothing to do with reactivity. Right, you have symmetrical ethers. So both groups bonded to the oxygen are the same. Basically, you have a plane of symmetry that goes down your oxygen. Right, so either side of the oxygen is exactly the same. So these are symmetrical ethers. Then you have unsymmetrical ethers, which you might be able to guess. The groups bonded to the oxygen are different. Oops, go away. Right, so you just don't have a plane of symmetry down your oxygen. Right, so you can't just fold the molecule in half at the oxygen and have both sides be the same. This has nothing to do with how they react or anything. It's just, you know, it's just the way we've classified ethers for a long time. It's like, oh, that's a symmetrical ether. It's like, okay, cool. So, what's good for you in the part of organic chemistry where we're learning a bunch of reactions is ethers are not reactive. Right? They don't do a whole lot of reactions. Like I only have like 3 or 4 reactions to teach you for ethers. Right? Because they're not very reactive, they're often used as solvents in reactions, right? They're what we dissolve other more reactive things in to react, and they ignore the ether. So we've seen, right, where we've used maybe ether, right? So diethyl ether just gets shorthanded to ether as a solvent. That's a pretty common solvent. And then one that we've 100% used, THF, right? THF is one of our polar aprotic solvents. All right, it's an ether. Other things are going to react, but THF is not going to react. Right? They're not particularly acidic. Right? These hydrogens here you'd think would be the most acidic hydrogens. Right? Oops. I got actually great words. The robots are coming to get us, everyone. So these hydrogens have roughly the same acidity as you'd see in like butane. So if you were comparing these 2 hydrogens on butane to the 2 hydrogens in diethyl ether, they're roughly the same acidity, right? You wouldn't think of butane as being an acid. And same thing with ethers. We don't really consider them to be acids in any way, shape, or form. So they're not acidic. They don't really do any reactions. So they're really good solvents. So we have like I said, we have a handful of reactions that we need to know with these. So nothing too complicated. All right, now old man fights with technology is next up here. Let me share. Okay, so we're going to talk about some examples of ethers. Cymbalta, I think Cymbalta puts you to sleep. I don't remember. They used to be commercials all the time. Now I forget, right? But it has this aromatic ether right here off of this naphthalene here. THC, it's the happy part of weed. It's part of weed that gets you high. CBD, all the rage in the world. You break that bond. That's the difference between CBD and THC. Is you break this carbon oxygen bond, and there's a double bond here. So that's the difference between THC and CBD is just opening that, is breaking that bond. And a lot of times, you make CBD as like a as an artifact of trying to distill out THC. You'll break that bond as you heat it. You also can actually make different strains of marijuana that make more CBD than they make THC. So you can like basically, you know, select for strains that you get more CBD out of because you're only allowed like a certain amount of THC in your CBD before you're not allowed to sell it. This one's cheating, 100%, right? Because these really aren't ethers, right? It breaks to the rule, but I like this structure. So, right, ether-ish bond here, right? This is artemisinin. This is an anti-malarial. It's one of the few anti-malarials that's been discovered in like the last 20 or 30 years. It had been a folk remedy for years. One of those like, hey, chew on this root and you'll feel better kind of deals. And they went in and they isolated this molecule.
So the mechanism of action here is that the uh, parasite gathers up a bunch of heme to try to break it down, right? It's in red blood cells. And the iron in the heme will break this oxygen-oxygen bond, which generates free radicals, which then damages proteins in the parasite, resulting in its death. So the question was, so chewing on a root worked?
Yeah. I mean, that's where aspirin came from, right? People were like, yo, chew on this bark if your head hurts. And then we went and like went through and like figured out what was in the bark and went like that one. We made it and we're like, oh, that's a part of the bark that you want to get when you chew on it. So we have aspirin. Taxol, which is an anti-cancer compound, comes from the bark of yew trees. And in the early 80s, we almost eradicated the yew tree from the face of the earth because it's a really good anti-cancer compound. And so we just started stripping the bark off of all the yew trees in the world. Funnily, trees can't live without bark. Not a biologist, but I knew that one, right? So, and we were really bad at making it, really bad. So what they were doing when people were making it was like in academic labs, they would get so far and they would run out of material because it took so many steps to make. And then they would take the actual Taxol and then break it down, like degrade it to the structure they had already made, and then start going forward again. Someone made some money off of this. You can get 95% of the structure of Taxol off the leaves of the yew tree. But that last 5% is what separates it from working and not working. This guy from Florida State figured out how to put the last 5% on super easy. Now he's a millionaire. But so now we isolate it from the leaves and then do basically one synthetic step to turn it into something that's not use doesn't work into something that works. But a lot of our medicines have come from folk remedies that we've then like gone and figured out what in that folk remedy is what actually does the actual work. And then we might like try to improve on that structure from there. But yeah, there's a lot of stuff like there's a whole field of chemistry that is natural products isolations where people go like scuba diving and they find like sea sponges and they grind them up and they find the molecules that are in them. They find like a tenth of a milligram and figure out what the structure is. And then people like me will then make them and see what they do. Like, you know, antibiotics, like what penicillin, you know, comes from grinding up a mold, right? Same kind of deal. There's a molecule just got published the other day. I got to read the paper still. That it only is made from a symbiotic relationship between a sea squirt and something else, and that's the only way you've ever been able to isolate this molecule is from this symbiotic pair. And so it's a really potent anti-cancer molecule, and someone just figured out how to synthesize it. So we don't have hopefully have access to them be able to study it because we can't go like harass a bunch of sea squirters and like see if they have a little symbiotic buddy that's making this molecule. Right. So this last one here, is monensin. This block of text beside it is the actual IUPAC name. So anytime you complain about a naming question, it could always be worse, right? So you've got, let me see here, you've got this ether here, this ether here, right? These are not quite ethers because there's an oxygen bond right beside the oxygen, but these two here. So what monensin does is monensin is a molecule that's just the right size that it will sequester sodium. So one organism will make this, secrete it, and will then it gobbles up all the sodium. So then the other organisms around it can't have access to sodium. So if you change the size of this, so basically what happens is the sodium, right? A sodium ion is positively charged. All these oxygens here have lone pairs on them, right? So they're negatively charged. So that sodium fits right in here, and all these oxygens will grab that sodium and hold on to it. And organisms have basically been able to change the size of this molecule, and you can fit different ions in different versions of this. You can fit lithium, you can fit potassium, depending on how long this chain is. All right, there you go. There's fun story times. So I'm gonna go over naming cyclic ethers, but let's do like a quick 10-second review on just naming ethers. Right. So if you remember, ethers are named just like substituents, so they go in front of the name of the longest chain. So like here, this is 5 carbon, so this is pentane, right? And now the ether name is the name of the beginning of the name for the number of carbons on the chain bonded to the oxygen. So it's 2 carbons, right? Ethane. You keep the F, and then to say that there's an oxygen, you put oxy. So it's F oxy, right? You can think of it as, right, you have your 2 carbons is your F. There's an oxygen between those 2 carbons on the longest chain. That's the oxy. And then you have your longest chain, right? You 100% have to put the 2. We were getting there. But yes, you 100% have to put the 2. So this would be 2-ethoxypentane. So you just treat it like a substituent. So this would be 3-methoxy 1,1-dimethyl cyclohexane. Did a bad job here. This is a wedge. So what would go out in front of this whole big name? Yeah, which one? It is R. So you say,
The question was, why are the two methyl groups numbered 1?
so the reason the methyls are 1 is you think about the hydrogen is 4. If you think about it, right? If I start at the one of the methyls with number 1, what's my next number? 1. If I start as the methoxy is 1, my numbers go 1, 3, 3. Where if I start at the dimethyl, I get 1, 1, then 3. So no matter how you number, you're going to have 1 and 3. Now you need to make sure you have the lowest possible numbers for the second substituent, which is the methyl that is shared by that carbon. Fair? All right, we remember how to name ethers. So straight chain ethers are pretty easy, right? You just have a substituent. Now we have cyclic ethers. And cyclic ethers are just this god awful collection of common names, right? So an ether with a 3-membered ring is an epoxide or, so right, oxirane. So there's two different conventions for naming epoxides. I'm going to teach you both so that you can kind of use whichever one is easier for that particular molecule. Right. We have oxetane, which is a 4-membered ring. These are like super duper hard to make. Um, we have THF, which is tetrahydrofuran, right? So poor THF didn't really even get its own name. So we have this, which is furan, right? What's the difference between furan and THF? You got rid of 2 double bonds. To get rid of a double bond, you have to add 2 hydrogens, right? So they were like, oh, if we add 4 hydrogens to furan, we get this molecule. Well, let's just call it 4 hydrogen furan. Okay, tetrahydrofuran. Cool name. And then the last one is pyran, which is a 6-membered ring. We are only going to really focus on naming 3-membered rings. So our focus is going to be on naming these. So there are 2 methods for naming epoxides. So first, there's the epoxy. We're going to treat the epoxide like a substituent. So you're going to name your parent hydrocarbon, your longest chain, and then you're going to have the epoxy out in front like a substituent. So this is epoxy pentane. Name your longest chain. Now you have to say which carbons your oxygen is bonded to. So your oxygen is bonded to carbon 2 and carbon 3. So it's 2,3-epoxy pentane. Now someone had asked if you have to have the oxygen on adjacent carbons. The answer is yes, because if the oxygen is not on adjacent carbons, it stops being an epoxide, right? So I can't have a 2,4 epoxy, right? Because the oxygen's too far apart. I have too big of a ring, right? So your oxygens always have to be on adjacent carbons. So it's always going to be 1, 2, or 2, 3, or 3, 4. It can't ever be 2, 4, or 2, 5, or anything like that. So it is a little bit different than like double bonds, right? Double bonds, we just kind of assume that if the double bond was at 2, we knew it had to go to carbon 3, right? But for whatever reason, epoxides, they do them differently. And they're like, you've got to give us both numbers. You can't just say it's 2 epoxy and just assume it goes to 3. We want both numbers. And again, the reason is rules. I don't know. Okay. Here, again, you're going to have 1,2 epoxy cyclohexane. So what would this be? Yep. So 3,4 epoxy, 3-methyl hexane. So we're going to number in this direction, right? We picked that direction because that puts the methyl group with the lowest possible number for it. Because either way we number the epoxide, it's going to be 3,4. So the methyl is what decided it. Not too bad, right? The oxirane method is the other way we name epoxides. Here you treat the three-membered ring, or treat the epoxide, as the parent hydrocarbon, right? So just like you would say cyclohexane and then list of substituents coming off of the cyclohexane, we're doing the same thing, but with the three-membered ring. Right, so our parent hydrocarbon isn't the longest chain, it's the three-membered ring. So we call the three-membered ring an oxirane. And then you list the substituents that are coming off of it. So it'll be an ethyl and a methyl. And then we have to number this to say, which carbon has which group. So when you number epoxides, or when you number oxiranes, the oxygen is number 1. So now it doesn't matter which carbon's 2, which carbon's 3, right? You do that based on the numbering rules you would have for a regular ring. So here, either way I number, it's going to be 2, 3, or 2, 3. So I'm going to want to put the ethyl group as being 2, since it comes first alphabetically. So this will be 2 ethyl, 3 methyl. What would that be? Again, as an oxirane. Yep. 2, 2, 3 trimethyloxirane. So whichever one is easiest for whatever molecule you're using or naming is fine for you to use. The one thing I will say is if you have a ring, always use the epoxy way, because I can't tell you how to name it if you try to name it as an oxirane. Right? I think it's just way harder. You've got these two rings fused together. It's just easier to have a substituent and say, hey, it's 1,2 epoxy, 1-methyl cyclopentane. So when you have a ring, just default to the epoxy. But the other two, either way works. Again, because your test is multiple choice, you probably need to know both ways, depending on which way I decide to make the right answer. but whichever way works. Fair? I think it's relatively easy. So we're gonna do like a quick review of all the ways you know how to make ethers. I made it sound like there's a lot. There's like three. Great. The Williamson ether synthesis is something we did right at the end of like substitution elimination chemistry, right? That's where you have an alcohol, you use a base like sodium hydride, and then you will use a halide of some sort to make an ether. Right, so your base, there's kind of two bases that get used. And this one's kind of a base in air quote. You can just use sodium metal and it react with your alcohol and make the O minus. The drawbacks or the limitations of Williamson ether synthesis, right? Oops. Right. You can never have a tertiary carbon on your oxygen, right? Because this is doing an SN2 reaction. If you make an O minus and you try to add it to a tertiary halide, tertiary halides don't do SN2 reactions, right? So that doesn't work. And if you have a tertiary group on your oxygen and your oxygen is negatively charged, like tert-butyl oxygens, like tert-butoxides, they don't do SN2 reactions, they only do eliminations. So there's no way that you can use a Williamson ether synthesis to make an oxygen that has a tertiary carbon on it. Right. To get around that, we have the acid catalyzed ether synthesis, right? This is where you take a double bond and acid and an alcohol and do effectively a hydration reaction. Here, right, it's pretty easy to get tertiary carbons on your oxygen, right? Because they make the most stable carbocations. So they're easy to make if you have them on if you have it set up that it'll be a tertiary carbocation from your double bond, right? The limitation here is, right, you have to worry about rearrangements, right? You always have to have that in the back of your head, right? That if you had this, right, you would end up making that. Right? Rearrangements. Boo. Right. So right, what happens here, I'm gonna give myself some more space, is, right, you have your protonated alcohol, you make your carbocation, right, before your oxygen has a chance to add, right, you have to check, you're like, oh, I'm a secondary carbocation, can I rearrange somehow? You can move this hydrogen. Now your carbocation's there, it's tertiary, right, secondary to tertiary carbocation. Now your oxygen adds, right, I guess we'll just draw the whole thing out because we're in too deep. Great. So we always have to be worried about carbocation rearrangements when we do these acid catalyzed reactions. So what can we, what do we have at our disposal to avoid carbocation rearrangements? That's where we use the oxymercuration reactions. Right. People are still scribbling. I'll give them a second. All right. And then the last one is oxymercuration. This eliminates your rearrangements. So this one, right, you never make a carbocation, but you have to use mercury instead. Right, so you use mercury trifluoroacetate and whatever alcohol you want. And usually you have THF as a solvent. Use sodium borohydride and hydroxide. And here you don't make any carbocations, so you're just able to add your oxygen to the most substituted carbon of your double bond. Bless you. Upside, no carbocation rearrangements. Downside, mercury kills you. Yeah, trade-offs. But it didn't rearrange, so hey, can't complain too much. Okay. So these are the 3 ways that you learned how to make ethers in Organic 1. So with that, we're going to pick up next time with basically reactions of straight chain ethers, and then we might get to the synthesis of epoxides.
Bye, 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 bye. Bye.